All right, so let's do this. So today we're going to be continuing our discussion of kinetics. All right, just kind of a little bit of a preview here about the next 2 weeks. This week we will be finishing up this chapter on kinetics. We got a topic today and a topic on Thursday as well. And then next week you will have your first exam of the semester. It will be only on this chapter here, on this kinetics chapter, all right? It'll be on Thursday of next week. During lecture in next week, we're going to have to start in on that next unit on equilibrium, but that will not be featured on that exam. The exam will only be the kinetics chapter, all right? And then in lab on Thursday is when you'll be taking your exam. Does that make sense? Cool. Next week. Yes. All right, so today our conversation is going to revolve around what's called collision theory. All right, and this is a pretty elementary stab at why it is that reactions occur. All right, that turns out to be a very, very, very complicated question. But sort of the simple understanding of why reactions occur is because of collisions between reactants, right? So reactions occur due to collisions between reactants. All right, I can tell this is going to trip me out. Sorry, reset. Okay, so there are like these three postulates of this collision theory that we're going to go through here. All right, so number one, the rate of a reaction is proportional to the rate of collisions. We can even say of collisions between reactants. All right, so why do chemical reactions occur? Well, they occur because reactants are smacking into one another. All right, we can kind of say this in a little bit more fancy math speak by saying our reaction rate, and then using this fancy little symbol here. It's kind of like a 3/4 of an infinity sign, which means is proportional to. The number of collisions that happens in a given time interval. All right, so the big brain scientists, they're kind of trying to come up with an understanding about why chemical reactions occur. It's a very difficult question, but at the very base of it is the fact that these reactants, have to be colliding with one another, and that's what's kicking off this chemical reaction. All right, so our second postulate here is about the orientation of these collisions. All right, so how exactly reactants are colliding with one another. All right, so we say reactants must collide with the correct orientation to form new chemical bonds. right, so what does that mean exactly? Okay, let's take a look at an example chemical reaction here. We're going to take carbon monoxide. This will react with oxygen to form carbon dioxide. Okay, we should be good and balance this chemical equation. All right, but let's take a look at our structures here. Okay, I'm going to draw these these molecules here using these little marbles. So carbon is going to be my black marble, and oxygen is going to be my red marble. So this is my molecule of carbon dioxide right here, one carbon atom bound to one oxygen atom. All right, if I have oxygen gas, that molecule's O2. So I'm going to, again, draw two oxygen atoms bound to one another. All right, and then in a molecule of carbon dioxide, if you remember back from our discussion of Lewis structures, what we have is a carbon in the middle, and the two oxygens are sitting on either side. All right, so these are our structures of our molecules here. And if we're going to quickly play the spot the difference game, what new bonds are we going to need to form on our product side here that we don't see on our reactant side? Yeah, so and between which two atoms? Carbon and oxygen, right? So this carbon over here is missing this additional oxygen atom, right? So that's my new bond that's going to need to form in this chemical reaction. All right, well, these are gas molecules. They're flying around, they're colliding in with one another, and we're going to see if this reaction occurs. So let's look at one collision. Okay, we're going to take our carbon monoxide molecule, and we're going to ram it into this oxygen molecule here in this head-on fashion, right? So the oxygen atom is going to go sailing in to this molecule here, okay? Will this form the correct bond that we want to form in this reaction? Do we want to form a new oxygen-oxygen bond? No. So this collision right here, we would call an unproductive collision. All right, this can't possibly lead to the formation of that new carbon-oxygen bond. All right. So now let's take a look at another collision. But this time we're going to swap them. All right, so now if we smack these things into one another, do we have our chance for our new carbon-oxygen bond to form? Right, so now we have the two correct atoms that are colliding with one another, or what we would call a productive collision. Okay, so the bottom line is not all collisions are created equal because there are specific atoms that are going to be bound together in our products. And we need to make sure that the collision is happening between those two atoms when our molecules have this correct orientation in space. Okay? Molecules are always just freely tumbling around. They will sample all possible orientations randomly, all right? But there's only going to be a small subset that are actually going to lead to productive collisions. All right, so we have this orientation factor in our collision theory. All right, so then the last one here, those colliding reactants, okay, that collision has to have a sufficient amount of energy in order to break all those old bonds that we're trying to break and to form the new bonds that we're trying to form. All right, so we're going to say colliding reactants must have a sufficient amount of energy in order to break our old bonds and start our electron rearrangement. To the new bonds. Okay, and this is kind of a key of an important thing to understand about chemical reactions. Chemical reactions are all about making and breaking bonds, and those bonds are made up of electrons, right? So when we're talking about a chemical reaction, we're really just reshuffling where the electrons are in our molecule, okay? So that's kind of the interesting bit, is what's going on with those electrons and how they're being rearranged. The protons and the neutrons, they're not doing much. They're kind of just sitting at the very middle of that atom. All right, cool. So this is kind of our three pillars of this collision theory, which again is kind of a first stab at answering the question of why reactions occur. And their simple explanation was, well, they occur because reactants are colliding with one another. All right, and they went a little bit further to say that the rate of the reaction is going to be proportional to the rate of the collisions between reactants. Okay, not all collisions are created equally. Those reactants have to have the correct orientation in order for these new bonds to form. Right? And not only that, but they have to have enough energy in order to break all those old bonds and start that process of rearranging electrons. Okay? So these are our three pillars of our collision theory. Okay? So we're going to try to understand reaction kinetics and stuff about energy by using what are called energy diagrams. These are these curves that you kind of see all over chemistry. So we want to make sure we understand what's going on when we see them. All right, what we're going to do is draw a graph. And of course, we're going to be good and label our axes. This one right here, we're going to label with energy. Now we're going to be a little bit more specific, thermal energy. Okay, and the bottom here is what we're going to call reaction progress. Our x-axis is reaction progress. So this diagram is going to tell us how the energy changes as this reaction is occurring. Okay? These curves always have this same sort of similar shape to them. All right, so you'll see these curves all over chemistry here. All right, so at the very beginning, on the very left-hand side of my curve here, this is when I have no reaction progress, or this is the energy of my reactants, when they're all by themselves, before any sort of reaction has occurred. All right, then we kick off this reaction, and that energy goes up. It absorbs energy, but then we also get a release of energy before it sort of ends up at this little tail over here, which is when our reaction is complete. Reaction progress is all the way at the end here, right? And so that means that over here is the energy of our products. Okay, so again, this diagram here tells us how the energy is changing as the reaction progresses. From reactants, it goes up, then back down to our product's energy. Okay, so when we looked at these curves previously, so it would have been like in our thermochemistry chapter, we focused on the difference between the energy of the reactants and the products. All right, this gap here is what we called the delta H, or the enthalpy change of this reaction. All right. In this particular case, this diagram shows me that my products are at a lower energy than my reactants are. So this would be a reaction that releases thermal energy or has a negative delta H. We had a fancy word for reactions that release thermal energy or have a negative delta H. Does anybody remember? Exothermic. Awesome. All right, cool. So this diagram right here illustrates an exothermic reaction. All right, and you can tell this reaction is exothermic by only paying attention to the two endpoints here, okay? We're going to talk a little bit more about this when we're going to revisit this delta H business when we talk about all the thermodynamic variables. All right, so we're kind of going to come back to this delta H business. But importantly, the only thing that matters for thermodynamics is where you start and where you finish. But for kinetics, what matters is what's going on in the middle here. All right, so now we're going to talk about this hump in the middle. This is what we call the activation energy. So this gap right here, starting from my reactants and going to the very peak of this curve here, this is what we call our activation energy. Okay? And the way that we think about this activation energy is it's this barrier that needs to be overcome for our reaction to occur. Okay, so remember that third postulate in our collision theory was that these reactants have to collide with this sufficient amount of energy in order for the reaction to occur. That's kind of what this little hump, this little barrier represents. What we imagine is our reactant is a little marble over here, sitting at this energy level. And it's really trying to make its way over this hump here, right? The only way it can do it is if it has a sufficient amount of energy to clear it up, and then it can go down over here to the product side, right? So in order for this reaction to occur, these reactants have to overcome that activation energy barrier. If they don't hit with quite enough energy, they just roll back down and we're stuck on the reactant side. All right, so this is this little barrier that we need to overcome in order for this reaction to occur. Okay? All right, so now we're going to compare two energy diagrams here. Whoa. So thermal energy, reaction progress. Okay, and we're going to compare these two graphs, and they both are going to start and end in the exact same place. All right, but one of them is going to have a very large activation energy barrier, and the other one is going to have a very small activation energy barrier. Okay, so to be clear, that both of these reactions are exothermic, same delta H because they begin and end in the same place, but we have this one on the left-hand side here, where if we measure the height of that activation energy barrier, Again, this is our large activation energy. And if we look on the right-hand side, we have a very tiny activation energy barrier. Okay? So one of these diagrams represents a very fast reaction, and the other one represents a very slow reaction. All right, so let's try to think about it here. We're our little marble. Are we going to have an easier time overcoming this very large activation energy barrier or this very small activation energy barrier? Which one of these reactions is going to proceed faster? The one on the left or the one on the right? The one on the right. So the small activation energy barrier, this corresponds to a fast reaction. And the one on the left, this would correspond to a slow reaction. Right? So the height of that activation energy barrier tells us about the kinetics, or how fast or slow our reaction is occurring. All right. So before we move on, let me maybe we should do an example real quick of a free energy diagram that is instead endothermic, just so we can make sure we know what that looks like. Or I guess I kind of gave away the punchline. What's a positive delta H called? Endothermic. Okay, cool. Let's just make sure we got what a curve should look like. All right, so the bottom line here is that now, again, we're only focusing on our two endpoints. Now our reaction is going to start at a lower energy level than where it ends. Right, so again, here is the difference between my reactant energy and product energy. This is a reaction that will have to absorb or have a positive delta H, which again we called endothermic. Okay, then everybody take a second and draw in where our activation energy is on this graph right here. All right, so activation energy, again, starting at that energy of our reactant and going to that very peak of that curve. This would be my activation energy. Okay, this is the barrier that our reactants have to overcome in order to go from reactants to products. Okay, and we'll talk a little bit more about this, but most reactions that are spontaneous are not endothermic, and you can kind of see illustrated why here. The forward reaction, you have this huge activation energy barrier you have to overcome in order to get from the reactant side to the product side. But going back, it's not quite as large. Right? So this is kind of our first little clue as to why these endothermic reactions are more rare. But again, that's just a fun little teaser for where we're going here. We'll talk more about that when we get to our thermodynamics chapter. Okay, cool. So the big brains in the physics and chemistry departments got together and started doing some theoretical chemistry with this collision theory, and they arrived at this equation that ties in this concept of this activation energy into our understanding of kinetics, what we call the Arrhenius equation. Okay, so our Arrhenius equation, let's just get this down and then we'll talk about what these variables are. All right, we have K equals A to the E to the negative EA over RT. All right, so we got a lot going on here. In this kinetics chapter, what do we think this K represents? Our rate constant. Okay, this is equal to A, and for right now, we're just going to call A some constant. We're going to go back and revisit this at the end. For right now, we don't know what it is. It's just some constant. No. K is equal to A times E to the negative A over RT. But yeah, A is just a constant. We're just going to call it some constant for right now. We'll talk about its meaning later. Okay. E is this magic number in calculus. It's kind of like pi. It's got some value, 2.67 or something like that. Whatever, it's a button on your calculator, okay? We have our EA, which is now we know our activation energy. All right, what about capital T? Temperature. So time we usually use lowercase t, temperature we use uppercase T. Okay, and let's just note that all this theory is kind of derived using the same math that our ideal gas law is derived from as well, which means that our temperature very necessarily has to be in units of Kelvin. Okay, all those kind of fundamental theories in chemistry have to use that fundamental unit for temperature, which is Kelvin. And speaking of the ideal gas law, what do we think R is? That constant, that ideal gas constant. Yes, this comes up again. You see it a surprising number of places in chemistry. All right. Ignore this for a second. Okay, so our goal is going to be to figure out, to solve this Arrhenius equation here, okay? In particular, what we need to find when we solve our Arrhenius equation is that activation energy, right? That's what we care about. How big is that energy hump that the reactants need to overcome in order to get to products? And we're also going to need to figure out what that some constant A is as well, all right? And we're going to do this in a very similar way to how we approached our rate laws, all right? So solving the Arrhenius equation. All right? And the way that we're going to solve this Arrhenius equation is by analyzing a data set, much like, again, like we did with our rate laws. All right, so let's say that I pick a temperature. we can do a bunch of experiments, a bunch of kinetic experiments, and find the value of that rate constant K, correct? Right? We did that in lab where we analyzed a data set and said, okay, I see what the rate constant is for that data set. All right? Then we're going to go back. We're going to crank up the temperature a little bit. We're going to repeat the process. What is our rate constant? All right? And eventually we're going to get this data set where we have our rate constant K versus time. All right? And so our goal is, again, to find these two missing components in this Arrhenius equation. All right, and why do we need a whole data set? Because we fall into the exact same problem that we did with our rate laws, which is that we have too many missing variables. Right? We can't just do one experiment and pick one data point. We have too many missing variables here. So instead, we're going to have to be clever with the way that we go about solving for this. All right, so step one is going to be to find, when we did rate laws, step one was to find that exponent, the order. Same thing here. Step one is to find that exponent, our activation energy. And just like when we were doing our rate laws, part of the trouble was getting rid of that other unknown variable. So we're going to use that exact same strategy where we take the ratio of this equation of two data points. All right, so should sound somewhat familiar. Okay, so again, what do I mean by take the ratio of two data points? Well, if I picked, let's say, I'm going to call it this data point 1 and this data point 2. All right, well, I know that for data point 1, that rate constant K at data point 1 is equal to A E to the negative activation energy over RT at data point 1. All right, but I can't just have one data point. I got too many missing variables. So what I'm going to do is divide this by the Arrhenius equation of my second data point. So K1 over K2 equals A E to the negative EA over RT1 divided by that Arrhenius equation for my second data point. All right, so we had to do this weird algebraic strategy. Why? What do we get to do here to simplify? Get rid of A, right? We get to get rid of one of those unknowns that we don't know, taking us down to just one missing variable here, right? So Y, so we can cancel A. Okay, cool. All right, so to be clear, what is it that we're solving for in this equation right here? The EA, right? So this guy right here, which is in these two places, which is kind of going to make it a pain. One trick, one algebraic identity that we're going to need to use here in order to make our lives easier, all right, is that anything to the x divided by that same thing to the power of y is equal to a to the x minus y. All right, so we can actually combine these two exponents here into just one all right, I would subtract the one on the bottom, but since it's already negative, that's going to make it positive. So this would be e to the EA over RT2 minus EA over RT1. Right? Because according to my little algebra rule here, I'm going to take the exponent on top and subtract the one on the bottom, but it's already negative, so this becomes positive. The other one stays negative. Okay, so I want y'all to take a stab at simplifying this and solving for that activation energy. One more thing, let's just say out loud, is we're definitely going to need to bring that exponent down. What are we going to use to do it? And in this case, it has to be natural log. Because we see that magic number e in there, that's when we know we have to use natural log. All right? Cool. So everybody take a stab at it, and then we'll do it together. All right, so let's make sure we got the same equation here. What we're going to need to do next is combine these two here. I got my variable in too many places, all right? So this uses an algebraic trick called factoring out. If I have something a times x plus a times y, this is the same thing to a times x plus y. We're going to factor that out. All right, so now my right-hand side becomes EA times 1 over RT1, I'm sorry, 1 over RT2 minus 1 over RT1. All right, if I wanted to go back, I would do what we would call distributing, right? Cool, and then if I need EA all by itself, what am I going to do? Divide by all this crap in parentheses right here. Okay, so I get my activation energy is equal to the natural log of that ratio of rate constants divided by 1 over RT2 minus 1 over RT1. All right, so now we have our activation energy. I'm going to copy that data set back down. All right, I want y'all to give it a shot at plugging this in. One thing that I want to make a note about with regard to order of operations is we got a lot of fractions going on in here. All right, so in order to make sure that we do it correctly, first of all, you definitely need to put parentheses around the denominator here, but also the denominators of these two as well, so that you keep both R and T underneath that divisor sign. All right. Oh, that's it. Yeah, gas constant. What the heck is that one? Okay, cool. Where do we find our ideal gas constant? On our handy-dandy conversion chart. And yes, there are multiple ideal gas constants, and the first two are actually what we used when we talked about the ideal gas law. What's the difference between these first two units-wise? ATM versus torr, just our pressure units, okay? But in this particular chapter, we don't care about pressure and volume and all that stuff. We want our activation energy. So we're going to use our units with joules in our ideal gas constant here. So our value for our ideal gas constant is going to be this 8.3144 joules per mole Kelvin. All right, so you will get a big number, okay? Our activation energy, and this is going to be one of those times that we're just going to conveniently ignore sig figs, and I'm going to say, let's 2 sig figs sounds great. We get 53,000 for our activation energy, okay? One of the things that you want to be careful of is you need to plug in the data point, K of data point 1, divided by the K of data point 2. But when you get down to the subtraction problem, it's temperature of data point 2 minus the temperature of data point 1. Whoops. Okay. Anyways, if you're having trouble getting it in your calculator, please let me know at the end of class. I'll look over your shoulder. We'll make sure we're punching it in correctly. I'll give you all a minute to do that. All right, and we get a big number here because that unit for the ideal gas constant that we used was in units of joules per mole Kelvin. All right, actually, if we're being good, joules per mole reaction. It's a little bit more convenient to express this in kilojoules per mole reaction. Okay, so the size of that activation energy barrier would be 53 kilojoules per mole. Okay. So we successfully did step 1, solve for that activation energy. Step 2 is solve for that sum constant A. All right, so let's take our data set here. Let's reset this. I'll get rid of my little markings. All right, our Arrhenius equation was that rate constant K equals A e to the negative EA over RT. But now I'm going to update this here because we did a little bit of work. I can plug in the value for that activation energy. I'm going to have to keep it in joules because of that our ideal gas constant, but our 53,000 is our activation energy. Okay, so let's look. Let's look at what we got here. That K given to us in our table. So is that temperature. As we said, we plugged in that value for our activation energy. And do we know what R is? Yeah, we always know what R is because it's on our constants page. So now you can see that the only thing missing here is that sum constant A. Right? So now in order to solve for A, we only have our one missing variable. We just need to pick one data point. All right, and algebraically it looks a little ugly, but all we're really doing is moving that E and its exponent over. So A is equal to K divided by E to that negative EA over RT. And you're going to get a big number. All right, so if we plug in our values here, we get A is equal to, again, I'm just going to pick 2 sig figs, 2.5 times 10 to the 7. All right, again, a very large number for A, which is very, very typical. What? I don't know. See me after class. We'll take a look at it. Oh, make sure your E is negative. You're raising to E to the negative 53,000. Because yes, E to the 53,000 will definitely give you an overflow error. Okay, we'll take a look. It's got to be the way that it's being punched into the calculator. A is going to have the units that match for K. And we don't actually know what K is, because we don't know if it would be different for a first order, second order, or third order reaction. We're kind of going to gloss over that. But yes, they would have to match exactly whatever K is. Okay, cool. So now we have this value for A, so now we've done it. We've solved our Arrhenius equation here. All right, let's talk about this A. We called it some constant A. Now we're actually going to give it a name here. A is what we call our frequency factor. All right, so our frequency factor has these 2 components to it that come directly from our collision theory, what we call P and Z. All right, Z is our collision frequency. Remember that first postulate said that the reaction rate is proportional to the number of collisions per second. That's exactly what this is telling you here, right? This is that proportionality factor. Number of collisions per second. All right, I'm going to organize this a little bit different. This is going to drive me nuts. Z is our collision frequency. Which is, again, the number of collisions per second. All right, in general, this is not necessarily something that's very easy to measure, but for gaseous reactions, we have a good rule of thumb value that we use for our collision frequency. So for gaseous reactions, Z is about 10 to the positive 9. All right, kind of just a good rule of thumb value that we use. All right, P, our other component of that frequency factor, is what we call our orientation factor. Okay, so P always takes on a value from 0 to 1. All right, and it is the fraction of collisions that are productive. Remember, by that we meant have the correct orientation? All right, so if you remember back to when we were talking, when we first introduced our collision theory here, we said that not all of our collisions were productive. They have to have that correct orientation in order to be a productive collision. That P is just a measure of what fraction of collisions are actually productive. That tends to be very small. So this value is very small, especially for large molecules. Okay, there are some reactions where P takes on a value of about 1. And that's if your reactants are simple atoms. Atoms, being small and perfectly symmetric, don't have any sort of orientation factor. All collisions would be productive, but generally speaking, the value of P is quite small. All right, only a small subset of collisions have that proper orientation. Okay, so in our data set, we found that that value of A was 2.5 times 10 to the 7. Let's go ahead and grab this. Let's remind ourselves that A has these two components, P and Z. And let's ask if the reaction is gaseous, what is the percent of productive collisions? All right, so we have our value for A, that 2.5 times 10 to the 7. All right, if we want to know about the orientation, which one of these are we solving for? P. So we need to know what Z is. How do we know what Z is? It's a gaseous reaction where we can approximate Z with that 10 to the 9 value. All right, so we have A equals P times 10 to the 9 for gaseous reactions. So we can plug in that value. So P is equal to 0.025. All right, that's the fraction of productive collisions. We have gotten very used to liking to look at numbers in percentage form. So if we want to percent P, we got to take P and multiply it by 100, right? Our fraction multiplied by 100. So our percent of productive collisions would be 2.5. Okay? All right, so we have our energy diagram here, kind of building off what we learned last semester, where we were looking just at where we started and where we ended, which told us about how much energy was absorbed or released by that reaction. All right? We now introduce this new component, this activation energy, this barrier that has to be overcome in order for reactants to be converted to products. And then we introduce this quantitative theory about that activation energy, what we call the Arrhenius equation. All right, given this formula here, we can solve for that activation energy and our frequency factor given a rate constant versus time data set. All right, to solve for that, we had to do a very similar game to what we did with our rate laws. We have too many variables, so we're going to take the ratio of two data points. That allows us to get rid of one and solve for the only other one that's in there. I'm not saying the algebra is easy. It was kind of a pain in the butt, but we got there. All right, once we have that activation energy, then we can solve for that frequency factor A. All right, picking one data point and plugging in everything else. That frequency factor has these two components, a collision frequency as well as our orientation factor. All right, collision frequency, if it's a gaseous reaction, we can use that value of 10 to the 9, and that allows us to solve for our orientation factor, or in other words, to figure out what was the fraction or percentage of collisions that was productive in that reaction, right? So given this reaction, we collect all this data, and this is this information that we can find by solving it through that Arrhenius equation. Cool. All right, one more quick topic that we're going to go over. No math, so your brain can rest a little bit. This is the concept of a catalyst. All right. A catalyst is something that can be added to a reaction that will speed up the rate of that reaction. Say a compound. All right. An important feature of a catalyst is it is not consumed by the reaction. So it doesn't appear anywhere on the reactant side or the product side of your chemical equation because it's not actually being consumed in the reaction. All right, and the way that a catalyst works, the way that a catalyst is able to increase the rate of the reaction is because it decreases that activation energy barrier. All right, so if we want to draw a free energy diagram, or not free energy, a energy diagram here. All right, I'm going to make one of these curves. Is this an exothermic or an endothermic reaction that I've drawn here? So this would be exothermic, all right? And this is a pretty high activation energy, a very slow reaction. So now we're going to add so this is without a catalyst. So now we're going to add a catalyst in there. Okay? And importantly, it's not going to change the energy of our reactants or of our products. We're going to begin and end in the exact same place, right? How a catalyst works is just by decreasing that activation energy barrier. Okay. Cool. So catalyst, what we need to know about a catalyst, the definition of a catalyst is something that's added to a reaction that increases the rate of that reaction but is not consumed by the reaction itself. Okay? The way that it increases the rate of a reaction is by decreasing that activation energy barrier. All right, just sort of fun fact, some examples here. Okay. To be honest, you don't have to know these, but these just kind of interesting to talk about. First of all, catalyst, super complicated. It's not like anybody looks at a chemical reaction and is like, I know exactly what to use to catalyze this, unless you've already done it before. It is a trial and error kind of process. You throw everything but the kitchen sink and you're like, man, this one thing made it go faster. Thank goodness. Let's stick with that for forever. A good example are the transition metals are often used as catalysts to help facilitate the transfer of electrons. Transition metals, they got kind of these squishy orbitals that can accept electrons and give up electrons fairly easy, and they can kind of be involved in just helping electrons move from one species to another more freely. Okay, an example from biology. What do we call the catalysts that we use in biology all the time? Enzymes, all right? And you want to talk about the most complicated damn thing in the entire world. Nature is one complicated individual, all right? It has come up with some of the most creative ways that you can go about solving any sort of a problem. We're really kind of made up of all these reactions that are happening very, very slowly, and then our body kicks off these enzymes when we need them in order for those reactions to happen on demand. All right, so enzymes are proteins that speed up biochemical reactions. But there's like no one explanation for how enzymes work. Some of them will bind a substrate and bend it a little bit so its bond's ready to break. Other ones will put two reactants right next to each other in just the perfect orientation. Other ones will kind of create this charge environment that makes it more likely for electrons to flow, et cetera, et cetera, et cetera. Super duper complicated. I mean, very interesting. I'm not saying that you shouldn't go down that rabbit hole, but I have no one-size-fits-all explanation for how these enzymes work. They are very complicated beasts. But yes, those are what we call our proteins that speed up our biochemical reactions. Just like all all catalysts, they speed up those reactions by decreasing the activation energy barrier. All right, and yeah, that speeds up the reaction. Wonderful. Break. Cool. All right. We got one more topic to cover with regard